Welcome to Lab 9. In this week, we will study arguably one of the most complex subjects in exploitation, heap overflow. We have two learning objectives in this lab. After completing this lab, you will be able to recognize the design principles of modern heap allocators, and you should be able to identify security implication of each design choices. In this week's tutorial, you will write a simple heap exploit for the first time. This figure shows a trend of vulnerability in Microsoft product in each year. Each color in this graph represents the portion of each vulnerability classes. As I highlight in the screen, heap-related vulnerabilities such as user after free are becoming popular in recent years. In this week's lab, we will study security issues and exploitation techniques against the emerging heap-related vulnerabilities. Heap vulnerability include buffer overflow or out-of-bound read or write, which we have been exploiting in previous labs like stack overflow. However, these common attack vectors are much prevalent in heap object, and their consequences are much critical in terms of security. There are also heap-specific security issues such as user after free or incorrect use of their API. Heap allocators provide a very simple set of high-level APIs. Malloc, which return a pointer to the allocated object of the specified size. Free, which will reclaim the object that the specified pointer pointed to. Other than two core APIs, there are in fact many other APIs such as calloc or realloc, but for simpler discussion, we will focus only on malloc and free in this lecture. There are three main goals of heap allocators: maximizing performance, minimizing memory usage or fragmentation, and enhancing security. If you just pick one of these goals, it's easy to build an allocator that perfectly meets the goal. However, in practice, the design choices of modern heap allocators are to achieve all these goals at the same time, making their design inherently complicated. There are three security-related design choices made in heap allocators. Binning means the heap allocator tends to perform operation on the same size object as a group. In-place metadata means the allocator tends to avoid unnecessary lookup by placing related metadata nearby. Cardinal metadata means the allocator places the raw data such as pointer as it is. We will highlight the security implication of each design choices later in this lecture. There are various types of heap allocators having different goals for different usage and workload. But in this lab, we mostly focus on default allocator in Linux, ptmalloc. In ptmalloc, when an object is allocated, it will reserve a memory region for the payload as well as the metadata. The metadata is placed before the object so that given a pointer, we can quickly look up its metadata such as its size. Since the allocator enforces the alignment of object, we can represent additional information by using the least significant bits of the size. For instance, ptmalloc utilizes these bits to represent whether the previous object is in use or free. Malloc chunk is the structure that represents a heap object and its metadata in ptmalloc. One thing to note here is that other than the size element, there is another interesting element in the struct, previous size. The usage of previous size is very interesting and highlighting the way the ptmalloc maximizes memory usage. For example, when p, the previous in-use flag is 0, it means that the previous chunk is free and the previous size contains a valid size. In other words, the previous size is part of the payload region of the freed object. On the other hand, when p is 1, the previous chunk is in use, so the previous size element is not valid. In fact, previous size is now a part of the previous object. Not limited to previous size, there are other metadata that stay in the freed object region, such as a pointer to the previous and next heap object. For example, when an object is free, forward point to the previous object and backward element point to the next object. By having this chain, we can quickly enumerate the free object by following this chain. One important property of the heap allocator is the way it consolidates to free object, which significantly reduces the memory fragmentation. Whenever an object is free, it checks if previous and next objects are free as well. If that's the case, it combines two free objects to make a larger one. For example, in forward consolidation, it first checks its previous in-use bit. If the previous object is free, it calculates the object pointer by using previous size, which locates right before the size element. As a result, we have a large free object that combines these two objects. Backward consolidation works similarly. It first looks up the next object by using its own size metadata. To check if the next object is free, it iterates once more to check the previous in-use bit of the next object. If the next object is free, it combines two objects accordingly. Because of this consolidation, there become one interesting invariant. There is no two free objects placed next to each other in the heap space. Because of heap's complex internal mechanism, any buffer overflow might incur a critical consequence to the program. Not just manipulating the metadata of next object, an attacker can even create mock objects for their own benefit. One example technique that I like to share is called unsafe unlink. In this case, there are two objects allocated, P1 and P2, but there is an overflow on P1. After the overflow, it simply frees P1. When freeing in P1, as an attacker, we'd like to incur a consolidation with the freed object, whose metadata we can control. By doing so, we overwrite the size metadata of the next object to a negative word so that it iterates the next object in a reverse order. At the same time, we overwrite the next object's previous size to 0, indicating that the next object is free. Since the next object is now free, it attempts to consolidate the current object with the next one. What makes interesting are the forward and backward link in the next object that we can control. To consolidate, it unlinks P2 from the linked list between free objects. Since we can craft forward and backward link, we can incur a semi-arbitrary write. Specifically, by putting the forward element to a destination address minus the offset of backward element and putting the backward element to the value that we want to write, we can overwrite the destination with the value of our interest. Each recent mitigation schemes are also very interesting. It performs two checks. First, it checks if the size of the current object and the previous size of the next objects are same. Second, it checks the integrity of the linked list by checking the backward pointer of the forward object is pointing to the current object, similarly to the backward object. These are effective mitigation schemes in practice, but indeed is far from complete, because we can bypass these two integrity checks with the craft object, which we can find in one of our challenges in this week. In fact, unsafe unlink is a really tip of the iceberg. There are numerous variants of exploitation technique. If you're interested in, please check the provided references. I like to show two types of heap-specific vulnerability, usually after free and double free. These two vulnerabilities are in concept very easy to understand. In usually after free, programmers use a free object through a dangle pointer. It looks very naive, but in practice, the places for use and frees are far from each other, so it's often very difficult to spot the problem. What makes interesting is that when an attacker can control the content of the free object. This happens when the free object is reused by an attacker's control logic. For example, if a function pointer inside the free object is controlled by an attacker, it can cause a control flow hijacking attack. Double free is also very simple to understand. It simply frees the same object two times. To understand the security implication of double free, we have to understand another property of a heap allocator, the size-based binning. It means that the heap allocator like ptmalloc cache the free object in a similar size as a group. In a double free situation, ptmalloc caches the same object 2 times in the same bin. It means that 2 malloc calls might return the same object 2 times. If an attacker can control one of the pointer, the attacker can hijack the other object as well. Like use after free, attackers might be able to launch a control flow hijacking attack against this vulnerability. To access the tutorial, you first have to log in to the lab server hosting the Lab 9 challenges. So please find the exact information in separate material. In this tutorial, you will walk through the actual implementation of ptmalloc and write an exploit against a simple heap buffer overflow. In summary, we discussed design choices in heap allocators and their security implication. In particular, we studied the heap structures of ptmalloc as an example. In this week's challenges, you will learn how to exploit memory safety issues of heap allocations and their incorrect usages, such as use after free and double free. Happy hacking!